After recording last week's tutorial, it occurred to me that the technique I've shown belongs to a whole class of tricks that we frequently use in production when it comes to art directing, volumes or volumetric effects, or even particles. And today what I'd like to do is show you a bunch of these techniques, just random tricks that we might have been hinted at in some of our previous tutorials. But let's talk about them a bit more in detail. So what I will do here is I will create a grid, dive in there, and I'm gonna scale it to say 4x4, and have 40 rows and 40 columns, like so. And also what I'd like to do in here, and we're going to use the points from this grid in a volume trail sub that we will set up to advect by time to visualize the vector fields that we're going to build now. All of these techniques rely on sampling a curve and using a curve to model or modify a vector field. So let's drop down a curve sub here, highlight it, and in the viewport hit space and 2 to go on the top view. Let's use this handle here to draw a really coarse curve, something like this. Hit enter to complete it, and hit space 1 to go back to our perspective viewport. So to turn this into a proper curve, I'm going to use the resample node, wire this up, and set up the resample node to treat a polygon as a subdivision curve. So we can see now we get this subdivided curve here. Dial down the segment length a bit and highlight it. So you can see now we have a finely subdivided curve here. First thing that I could do, of course, is turn this into a VDB, either with the help of a polywire, which I'll wire up in here, maybe increase the divisions here to say 16. So I have this polygonal wire here, which I can then wire into my VDB from polynode, decrease the voxel size, and end up with the VDB storing this extruded curve. Also, what I could do is I could directly hook up a VDB from particles node underneath the resample node and use the individual points in my curve to define where my geometry is. However, in order to do that, I need to dial down my point radius scale to say 0.1, maybe increase the point count on my resampled spline by decreasing the segment length to say 0.01, and now I end up with something similar. Two techniques to basically arrive at pretty much the same output here. Let me just delete this here. Seems a bit more elegant here. And in here, what I'd like to do is dial up my half-band voxels, which is basically the padding of voxels around this surface here. And 3 voxels are really close to the surface and really memory efficient. However, we need a bit more space because we want to advect particles through a velocity field that we're going to build. So let's dial this up to say 64. This will calculate a bit, and you can see now my bounding box of my volume has grown a bit bigger. Now let's turn this into a vector volume, and again, I'm going to use my VDB analysis sub to do so. And I will leave this set up as is to turn this SDF into a gradient, but I want to change its output name to vel for velocity. And we could directly wire this into our volume trail and highlight it, and we could see something like this here, which already is pretty interesting. Because what we calculated now is the gradient of our VDB surface. That means kind of the normals of our surface. So each of my points on the grid will be advected according to the nearest normal that is in my volume. When we look at the geometry, let's highlight this and go to our volume trail. You can see that those volume trails here are always perpendicular to the SDF surface. So that's the first trick. Now, say if we want to modify this, how would we go about this? Well, let's drop down a volume VOP and wire this in after the VDB analysis here. Dive in, and the first thing we'd like to do is get rid of this node here and create our own bind export. And we'd like to export a vector called vel for velocity. And also we'd like to import this maybe for later. So use a bind here and again import a vector called vel. So the vel that we're importing here is the gradient that we just calculated. But how about rotating this vector around 90 degrees? Well, for that we can use the cross product, and we're going to wire in our velocity vector in the one port, and in the other port we can set up a constant. And for example, let's use a constant up vector, just pointing along the y-axis, and export that as our new velocity. And now we can see we arrive at this here. Our current gradient just turned around 90 degrees. And depending where our up vector is heading to, we can influence along which axis and how much our gradient is rotated. So let's set this back to be an up vector along the y-axis. And that is trick number 2. Let's go up one level and hide this geometry and just highlight our volume trail here. And what we could try now is kind of blend between this rotated version of the gradient and the original version of the gradient, depending how far from the actual surface of our geometry we are. And how far we are from the surface is actually stored in this SDF that we created here. So let's pipe this into our volume VOP as well. And within the volume VOP, we will need to drop down a volume sample in order to read out the values coming in through our surface SDF that we just wired up. So we will wire our input 2 into the file name slot here and the current voxel position into the sample position. So out of this slot we will now have the SDF's value. that stores how far away from a surface a given voxel is. So let's use that to drive a mix node that just blends between the original gradient and the rotated gradient. However, before we just simply pipe in our SDF value into the bias that drives how strong each of those input gets mixed into the output, before we do that, let's drop down a fit node first so we can adjust the range and the output range of our values coming in here. So let's wire this in. And I think I set this up to have a diameter of around 0.1. So I assume that my source minimum value will be -1 and my maximum value will be, well, the maximum distance that my volume will have to our surface. Set this to 0.5 for now. And now let's wire this into our bias slot in the mix node and use the mix node's output for our velocity. Let's go up one level and highlight the volume trail again. And we can see now this blending is happening between the gradient pointing in the normal direction of the surface and this rotated version of it, depending on how far away from the geometry center we are. So that is trick number 3. And of course you could tweak your fit node, for example, invert those minimum maximum values to adjust the effect to your liking. Okay, let's reset this and go up again. There's an interesting function in the resample node here that allows me, on the one hand, to calculate the tangent, that is a vector pointing along the direction of my spline here, and the curve u, which goes from 0 from the first point of the spline to 1 of the last point of the spline. And what we could do, for example, is use the curve u to actually drive the length or the strength of my velocity field that I'm going to use for the advection. So what I will do is drop down a volume wrangle, which I'll wire in below the VDB from particles here. I will write values into this VDB here, and I'm going to pipe that into the third slot into my volume bob. And also, I will wire in my resample spline here with the curve u and tangent u attrib written on it into the second slot of my volume wrangle. And now what I want to do within the volume wrangle is, first, for each voxel's position, I want to find the closest point on that spline that we're going to pipe in here. So the way I'm going to do that is with our trusty old near point function. So let's call this thing NPT. And NPT should store the point number of the closest point on the spline to that voxel. So let's use the near point function here. We're going to look for near points coming into the second slot. That's slot number 1. And we're going to look for points close to our current voxel position. That's the vector P. Next, let's look up the curve u attrib on the point we just found. So let's create a float. Let's call it curve u. And let's use the point function to look up our curve u attribute on the points coming in through slot 1 with the point number of NPT. And finally, let's write that out to our VDB. So let's just figure out what its name is. So middle mouse button on this, and we can see it's called surface. So of course I could rename this, but for simplicity's sake, I'm just going to store this float curve u value now in my attribute called surface. Not really clean, but for now, I mean, it's compact. So let's stick with it. In my volume bob, I will just take this volume sample here. Let's drag this out a bit. I will just copy this volume sample here and wire in not the second, but the third slot. So I'm going to read in the curve u value that I just written to the volume and use that within a multiply to scale the velocity vectors. So let's wire this up in here. And we can see something weird happening there. Let me just check and figure out what's going on here. Okay, so it's a common mistake that happens quite often with VDBs. What we have here are regions that have not been activated. So in order to prevent this, I'm just going to create a new VDB. It's going to be a fog volume. Let's dial down the voxel size to say 0.02. Let's call it curve u. And also after that, drop down a VDB activate to activate it. And we want to activate a region of say 4 by 1 by 4 units. And pipe this into our volume wrangle here and change our name from surface to curve u, like so. And now we can see we have a proper field storing our curve u value. So when we highlight the volume trail now, yeah, we see those errors gone, and we can see our trails changing in length according to where they are in regards to our original control spline. Let's maybe increase the trail length here a bit so you can see it a bit better, like so. Okay, that's trick number 4. And for the final trick, let's copy those 3 nodes here, paste them. I'm going to need a vector float volume. Let's call it vel for velocity again. And this time we will look for a vector. Let's call it tangent u. And it will be the attribute tangent u that we calculated while resampling our initial curve here. So let's write that into our velocity and wire it into our volume bob here which already looks promising, but let's dive into it and look at what's happening. So by piping in the tangent that we calculated from our control spline in here, let's wire this up directly to the output. We can see we get a field like this. Let me go up again and decrease the trail length so we can see it properly here. So what we're seeing here is a field that always follows the closest tangent that we have on its control spline. And this was the exact same trick that we used to generate the control field in our embroidery tutorial, which you might want to look up. Also, this is a main trick how you could do grooming for hair and fur, for example. So again, on the one hand, what we could do is again calculate a cross product, which will just yield the right angle towards this tangent, which basically is a form of our gradient that we could calculate differently as well. And of course, we could go through the mixing of those two values and also through the scaling. So that is trick number 5. And although all these techniques are not really intricate or not really complicated, when you combine them, you have the ability to really finely control how the vectors in your velocity volume will flow, and thus have the ability to very finely art direct what your setup will do. So no matter if you're using this to drive particles, to drive a smoke simulation, a fluid simulation, or to generate trails or geometry out of it, this is one of these setups that's really simple, that can be encapsulated and handed out to your artists. And just from my personal experience, I can tell you they are really happy to be able to just draw curves and be able to influence and drive the fields and the volumes that they will use to create astounding artwork out of the setups that you built. And that is a really rewarding thing to witness as a TD. So, as always, hope you're having fun with this. I'm especially looking forward to the kind of artworks you guys come up with using these techniques or a combination of those, so please keep sharing them. That's it for today, and see you next week.